Hello, my name is Tony Botting and I'm a simulation specialist at GoEngineer. In this video we'll discuss how you can interpret the results from random vibration RMS plots. As you might recall, for random vibration you can input a base excitation in the form of PSD input that is generated from a time history acceleration signal. Some components of output include RMS values of stress, displacement, velocity, and acceleration. You can generate a plot of RMS stresses, for example, as shown here. Now we just need to interpret the results. The time information is lost since the random vibration analysis calculates in the frequency domain. Additionally, the average value of stress is 0, so an RMS value is calculated to give a measure of the nominal stresses experienced by the structure. The RMS concept is analogous to that used for the alternating voltage found in most homes in the United States. The current actually alternates between plus 170 and minus 170 volts, and you'll notice the average is 0, but the nominal voltage, or RMS value, is about 120 volts. Note that this sine wave is obviously one frequency. This is quite different from a random vibration signal, which has multiple frequencies, but the concept to illustrate the RMS value is the same. This plot of stress shows what is called the RMS value. You can examine the structure for the maximum RMS value or look specifically at areas of interest to identify the RMS stress at that location. For example, at this component lead, the probe tool shows about 6,000 psi. If the average or mean value is 0, then the RMS value is also known as the 1 sigma value. From probability theory, alternating values between plus or minus 1 sigma can occur in the structure about 68% of the time. This table summarizes the probability statements you can make about the RMS results. The column labeled criterion can come from your customer specifications. There are multiples of 1, 2, and 3 of the RMS stress value of interest in the simulation plot. For example, many spacecraft manufacturers want their electronic components to withstand 3 sigma values. So you'll need to multiply the simulation values on the plot by 3 to report this case to your customer. Again, from probability theory, you can state that stresses will be between plus 3 sigma and minus 3 sigma about 99.7% of the time. Other equivalent statements you can make include the probability that the stress will be between plus 6,000 psi and minus 6,000 psi is about 68%. Alternatively, the probability the stress will exceed 6,000 psi is about 32%. For a 3 sigma criterion, the probability that the stress is somewhere between plus 18,000 psi and minus 18,000 psi is about 99.7%. Alternatively, the probability the stress will exceed 18,000 psi is about 0.3%. You can also perform calculations in terms of time. Suppose the structure feels this random vibration time history for 20 minutes. The 1 sigma RMS stress at this location is 6,000 psi. For what amount of time will the stress amplitude exceed 6,000 psi? The calculation is 20 minutes times 0.32, or about 6.5 minutes. You can also ask, for what amount of time will the stress amplitude exceed 18,000 psi for the 3 sigma condition? The calculation is 20 minutes times 0.0027, which equals about 3.5 seconds. In this video, we've discussed how you can interpret the results from random vibration RMS plots.